When you connect a large language model to a vector database, you are effectively mapping billions of data points into a searchable coordinate system. For simple, direct questions, this standard Retrieval-Augmented Generation architecture is highly effective. If you ask for a specific date or a clear definition, the system finds the exact document and generates a response. But as your dataset grows denser and your queries become more complex, a symptom emerges. The system starts returning documents that are tangentially related to the topic, while missing the specific context required for a correct answer. This happens because standard RAG systems rely entirely on vector similarity. That single mathematical operation creates a systemic bottleneck at the retrieval node, often blinding the language model to the most relevant information. There is a common assumption that massive context windows, models that can ingest hundreds of thousands of tokens at once, have made retrieval optimization obsolete. The logic suggests that if you can just feed the model everything, precision no longer matters. To actually solve this retrieval bottleneck, we have to move beyond a brute force approach. The solution requires a two-stage architecture using a specific type of transformer known as a cross-encoder to re-rank the data. Ignoring the architectural mechanics of how data is retrieved leads to hallucinations at scale, regardless of the raw processing power of the language model at the end of the pipeline. The root cause of poor retrieval lies in the offline, pre-computed nature of standard vector search. When you embed documents into a vector database, you are using an algorithmic foundation called a bi-encoder. A bi-encoder's job is to compress a dense document's semantic meaning into a single vector. All nuances of a multi-paragraph text are flattened into one isolated point on a scatter plot. The user's query is also converted into a single vector at runtime. The system uses a metric like cosine similarity to measure the spatial distance between the query vector and the document vectors. The dots closest to the query are deemed the most relevant. This creates a compression penalty. The document vector was generated weeks or months before the user ever typed their prompt. Because the bi-encoder had no knowledge of what the future query would be, it cannot prioritize specific semantic nuances that might be critical later. For example, in a database containing programming manuals and biology textbooks, a query asking how to install Python relies on general vector proximity. The system frequently returns documents about Python snake habitats simply because the shared keyword drives the vectors together. Pre-computing bi-encoders are blind to query-specific nuance, making them an inadequate filter for complex logical retrieval. Developers often try to work around this by widening the net. If the most relevant chunk of text is buried at position number 23 in the vector search, they simply retrieve 30 chunks instead of 5. This is known as context stuffing, overloading an LLM's context window with a massive, overfetched pile of documents in hopes that the model will find the needle in the haystack. This chart maps the two distinct metrics at play. The climbing line shows retrieval recall, which measures whether the database successfully fetched the right document. As you pull more data, retrieval recall goes up. The second line represents LLM recall, the model's ability to successfully extract and use that document. When you place crucial data in the center of a massive context window, LLM recall drops. The model is statistically more likely to ignore information buried in the middle. We can see this in action using an experiment on a dataset of technical patent filings. To ensure the correct patent was included in the prompt, a system was intentionally fed 30 retrieved chunks at once. The model failed to extract the right methodology. It hallucinated an answer by combining different patent references, while simultaneously tripling the API token costs for that single query. Attempting to solve retrieval by dumping raw data onto the language model often reduces system accuracy while significantly increasing operating costs. The algorithmic fix to this context stuffing paradox is a process called re-ranking. True re-ranking relies on a specific transformer model architecture known as a cross-encoder. Unlike a bi-encoder, which processes data in isolation, a cross-encoder evaluates the user's query and the document together at runtime. Inside the node, the transformer's attention heads draw direct connections between specific words in the query and the document context. This joint processing outputs an individual relevance score for that specific pair, rather than a generic spatial distance. Because it reads the text together, this architecture captures deep semantic cues. It can differentiate between a request for historical data versus recent developments, based entirely on the phrasing of the prompt. The model fires across its parameters, weighing every potential interaction between the user's intent and the source material. Cross-encoders bypass the compression penalty of static embeddings by allowing the model to evaluate the specific query against the specific document at full resolution. But this precision comes with a computational trade-off. Cross-encoding requires a full transformer inference step for every single query document pair. If you tried to run a cross-encoder across a database of 10 million documents at query time, generating a response would take days. It is not a viable tool for live search on its own. The two-stage pipeline is the structural compromise that enables high-fidelity retrieval at sub-second speeds. In Stage 1, we utilize the fast bi-encoder vector search to overfetch a wide candidate pool. In Stage 2, we pass that small shortlist to the heavier cross-encoder. It reorders them based on runtime relevance and sends the top 5 documents to the language model. Decoupling retrieval into 2 distinct algorithmic stages allows the system to utilize the velocity of vector math without sacrificing the semantic precision of joint processing. We can benchmark this trade-off using an experiment run on a dataset of machine learning papers. The system was given a technical prompt asking specifically why a developer would use reinforcement learning with human feedback, or RLHF. In this terminal output, the vanilla single-stage RAG architecture surfaced a generic definition of RLHF at position number 1. It failed to address the specific why of the question, but the two-stage re-ranked architecture found the context-specific answer about capability enhancements buried at position 23 and pulled it to the very top. There are production realities to this approach. Adding a re-ranker API introduces overhead, increasing latency from a few hundred milliseconds up to 1 or 2 seconds. External re-ranking APIs also charge per request, adding a marginal but real economic cost to each query. For enterprise systems dealing with complex data, a 2-second latency for a grounded, verifiable answer is a necessary trade-off to prevent the immediate failure of a sub-second hallucination.